Hi, my name is Xuefeng Song. Today, I'm gonna present our paper "Do Code LLMs Understand Design Patterns," which is done by Zhenyu Pan, Xuefeng Song, Yunkun Wang, Rongyu Cao, Binhua Li, Yongbin Li, and Han Liu, affiliated by Northwestern University and Tongyi Lab at Alibaba Group. I will move through 5 sections: introductions, related work, experimental design, result and figures, and conclusion and future work. First, the introduction. Code LLMs are great at code generation, completion, and repair, yet they often violate a project's established design patterns. We deliver the first systematic evaluation of that problem, offering an assessment framework, bias analysis, and practical guidance. Now, let me talk about some related work. Um, Prior benchmarks like Codex Glue focus on function accuracy. Families such as GPT-4, Cloud, CodeQN, and Llama 3 keep advancing, but none are judged on pattern compliance, leaving a clear gap. Now, the experimental design. We designed 3 tasks: pattern classification, which the LLMs identify patterns from code files; line completion, where LLMs complete 3 randomly removed lines based on the context. The last one is function generation, where LLMs generate functions from GPT-4 produced descriptions and context. For the line completion and function generation task, we tested models both with and without provided design pattern information to assess their understanding. Our evaluation covered 12 classical design patterns across Python and Java, using a dataset of 48 GitHub repositories at 3 difficulty levels. Performance was measured using accuracy, code similarities, and edit similarity. Now, this is the result we get from the pattern classification task. Um, from the figure, you can see that when identifying design patterns in code, LLMs frequently misclassify singleton and factory patterns due to their common overlapping features. Singleton centralized object management resembles facade, proxy, or command, where factory overlaps with abstract factory, builder, or strategy, especially in frameworks like Spring or Python's dependency injection. Real-world code often blends multiple patterns, increasing ambiguity. LLMs rely on static method, single instance queues, and creation logic, which are not unique identifiers. The facade pattern's abstract nature and subtle context cues make it particularly challenging. Improving training data and clear context understanding are needed. Um, as shown in this table, GPT-4o and Llama 3.1 70B achieved the highest accuracy, which is 38.81%. Llama 3.1 70B excels in Java's 53.33% overall, 55.56% hard, and 71.43% easy with GPT-4o. While GPT-4o lied in Python, uh, which it reaches 29.73% overall. On Python Easy, several models matched at 44.44%. Performance generally decreased from Java to Python and from easy to hard, indicating Python and complex samples are more difficult. Although GPT-4o and Llama 3.1 70B performed best, all models need improvement, particularly with complex Python code. Now, the following result is our line completion and function generation task. The table, as you can see in this table, um, first CS and ES relationship. Here, higher CS, which is the code similarity, typically indicates less editing, which means higher ES, but not always linearly. GPT-4o, for example, achieved high CS, yet it still required significant edits, especially in line completions. Second, the impact of design pattern knowledge and model variability. GPT-4o and Llama 3.1 405B often performed better without explicit pattern information, suggesting internalized knowledge. Claude 3.5 consistently generate accurate, adaptable code. Code queuing performed poorly. Function generation generally yielded better similarity than line completion, indicating stronger performance on larger segments. Improving pattern integration and task-specific optimization could enhance LLM reliability and reduce manual editing. From this table, you can see that it indicates design pattern information usually improves model performance. GPT-4 singleton accuracy notably increased, uh, 33.64% versus 13.2% when informed. Yet, exceptions, for example, GPT-4o is GPT-4o's better observer result without patterns suggest some models rely effectively on internalized knowledge. Patterns varied in difficulty, with template and decorator easier, while builder, bridge, and facade were challenging. Higher CS often implied less editing, which means higher ES, but cases like decorator revealed inconsistency. GPT-4o and Llama 3.1 70B performed well overall. Code Q1 struggled. From this, we can get some insights. High code similarity doesn't always mean lower editing effort, highlighting the need for future LLMs to better integrate design pattern knowledge, improving practical utility, reducing manual editing, and enhancing overall reliability and efficiency in software development. Now, let me do a brief conclusion and future work we will do. LLMs still struggle to respect design patterns. We need pattern-aware pre-training and smarter prompting. Future work will broaden datasets and metrics to cut developer post-editing and boost reliability. Thank you for listening.